So before we start to get into some of these really deep Nobel Prize ideas, let us try to gain a little more experience with what we're doing by considering a question about how we might apply this in a slightly different context. So here's the question, what should we do if we had a different potential instead? What if v of x was equal to, say, some constant a times a delta function potential plus a second delta potential function, not centered at x equals 0, but centered at x equals a. Suppose we had a potential like this. I'll draw a little sketch of the potential. So here we're plotting v of x as a function of x. And what we're going to have then is this very tall, narrow delta function of strength a sitting here at x equals 0. And another version of it, the exact same height, the exact same strength here, centered at location x equals a. So we can ask ourselves, how would we get the reflection and transmission coefficients, and therefore also the corresponding probabilities for a system like this? We can ask ourselves, well, what really would change from what we've just done? Now, if you think about the kind of processes that we are talking about, they are really the same, right? If we're computing transmission, we could go straight through. We could go straight through with one rebound, and so forth and so on. And likewise for the reflections, if I wanted to compute what the reflections would be like, let me put, this would just continue ... If we want to do the reflections, it's going to be exactly the same structure. The first case is just an immediate reflection. The second case is where we hit the back and reflect. And then we start to hit the possibility of multiple reflections and ricochets, and that's how we would then get the reflection coefficient from these terms and the transmission coefficient from these. And the formulas and really everything would be pretty much exactly the same thing. The only difference would be in the actual values of the corresponding fundamental coefficients. So, for example, what we would have to consider now are not the reflection and transmission off of an up step and a down step, but reflection and transmission off of just a single delta function. So we would have to solve this problem first. First we would solve where I just have a delta function here, potential v of x of a given strength a sitting at the origin, right? And then if I send in a unit wave of strength 1, there will be a certain amount of transmission T and a certain amount of reflection R. And certainly we know how to solve the delta function scattering. It's not, it's not particularly complicated. It's a little bit more involved than just the single step, but it's not really too bad. And certainly we could solve this. Now, the nice thing about the delta function is that it's a completely symmetric function. So also, if I have the unit wave coming in on this side, I know that it looks just like the original problem. The only difference is now I've just switched my x-axis. X goes to minus x, but my physics is invariant with respect to that, so I'm going to end up with exactly the same transmission and reflection amplitudes, regardless of which direction I'm heading in when I hit my delta function. Likewise, when my delta function is centered not at x equals 0, but is centered here at x equals a, it's a very similar story, right? Physics doesn't care about the origin of my coordinate system. So indeed, once again, if I send in a unit wave, there will be a transmission, and it will have the same transmission amplitude t as my original problem did, and similarly for the reflection coefficient r. And that's if I happen to hit the second delta function coming in from the left. If I happen to come in and hit it coming in from the right with a unit wave, it's the same story. It has the same symmetry of reflecting around this x equals a axis. The problem would look the same either way. So I just have really two coefficients for which I have to solve, r and t, and then I can apply the formulas up above. So the answer to this would be just the same formulas with then this r plus or minus that we had in the preceding formulas, now the pluses and minuses are all really the same. We could just call those these new r that we get from solving the single delta function potential. And then once we have these coefficients, we can get the final results. The last little bit we would need, of course, is the propagation factor. When I'm propagating between these two, my wave vector is just the same wave vector I have in all of my regions, right? When I send in at a given energy E, there's just the same wave vector K in all the different locations. So then the propagation factor, which is always just E to the IK, times the corresponding propagation distance. That propagation distance in between here is A, so it's E to the IKA. Then we can just use the same formulas as we had up above.